Now suppose that we have a square singular matrix A. Could we still decompose A to be equal to U sigma V transpose or not? Again, the constraints for those are U should be a square orthogonal matrix, V should be a square orthogonal matrix, and sigma should be a diagonal matrix. Can we still have a valid decomposition in this form? This form implies that A multiplied by V is equal to U multiplied by sigma, and this means that A multiplied by V1, V2 for the 2D case, this should be equal to some U1, some U2 multiplied here by some sigma 1, 0, 0, sigma 2. Could this still be possible or not? Suppose that we have a matrix like this, a rank 1 matrix where we have 1, 1, and 2, 2, just like that. In the non-singular case, we said that V1 and V2 belonged to the row space of the matrix A. But for this case, the row space is only one-dimensional. We can't have two perpendicular unit vectors in the row space of the matrix A. Now suppose that we drop this constraint. We don't want all the vectors right here to belong to the row space, but we still want them to be perpendicular unit vectors. In this case, we could choose V2 to be perpendicular to V1. We could say that V1 is equal to 1 over root 5 multiplied by 1, 2, because the row space is 1, 2. So I can choose V1 to be this vector right here and then choose V2 to be perpendicular to V1. It won't belong to the row space, but it will still be perpendicular to V1. Now, since V2 is perpendicular to the row space, we say that V2 belongs to the null space because the null space has all the vectors that are perpendicular to the row space. So in general, in this matrix V, I could have some vectors from the row space and some other vectors from the null space and still make this an orthogonal square matrix V. In this case, we will have that A multiplied by V1 will be some vector in the Coulomb space, and we can say that this is equal to sigma 1 U1. Now, what about the second vector V2? V2 belongs to the null space, so we need that A multiplied by V2 be equal to 0. But still, if we want this equation to still be valid, then we want this to be equal to sigma 2 multiplied by U2. So either U2 needs to be the 0 vector or sigma 2 needs to be equal to 0. Now, if we make U2 equal to the 0 vector, then this matrix U right here will no longer be an orthogonal matrix. On the other hand, if we make sigma 2 equal to 0, this matrix right here will still be a diagonal matrix as desired. So we could leave U as an orthogonal matrix and then put sigma 2, the second singular value, to be equal to 0 and still have this equation be a valid equation and a valid representation of the matrix A. Now let's have a look at this matrix U. In the non-singular case, those two columns belong to the Coulomb space of the matrix U. But in this case, the Coulomb space of the matrix U is only one-dimensional and we can't have two perpendicular unit vectors in the Coulomb space. So we choose U2 to be a vector perpendicular to the Coulomb space, which will belong to the left null space of the matrix A, the null space of A transpose. By this choice, we can keep the matrix U as an orthogonal matrix as we want and still have this equation as a valid equation involving the matrix A. So in this case, we will still have A multiplied by V, an orthogonal matrix, to be equal to U multiplied by sigma. This is an orthogonal matrix and this is a diagonal matrix, but we have some elements on the diagonal as zeros. Actually, this situation right here is why this is called the singular value decomposition and why those are called the singular values, because if some of those elements on the diagonal were zeros, this would mean that the matrix A is a singular matrix, a matrix with no inverse. Now let's look at the geometric interpretation of this case. Let's redraw our circle again. So we have this circle right here. Okay, and this is I cap, this is J cap, and we have here V1 and V2, two perpendicular unit vectors, like that. And suppose for this example that there are points inside the circle just like that, as I think this will make the visualization easier. And so this is the matrix X, and we multiply this matrix X by the matrix A, so that Y is equal to U sigma V transpose X. And this is equal to, here I have U1 and U2, here I have sigma 1, 0, 0, 0, and then V transpose, V1 transpose, V2 transpose, and here I have the vector X. This first multiplication right here will represent the vector X using the V1 and V2 bases. So we can think of this as representing the vector X as a combination of two components. One component is in the row space of the matrix A, and the second component is in the null space of the matrix A. After that, we multiply this new vector by this matrix right here. This matrix will keep the component in the row space and multiply it by sigma 1, while it will remove the component from the null space by multiplying it by 0. So after those two steps, you will have a vector like that. Here you will have sigma 1, V1 transpose X, and here you will have 0. Then you multiply this by U1 and U2. Then the final multiplication right here will give you this multiplied by the first column plus 0 multiplied by the second column. So this will be equal to sigma 1 V1 transpose X in the direction of U1. So this is a unit vector U1 which belongs to the column space of the matrix A. So here is what happened geometrically. First, we rotated this to have the following form. We had another circle, and we still have the data points, but now we have rotated everything such that this is V1 after rotation and this is V2 after rotation. So let's call those V1 dash and V2 dash. Then for all the points right here, we multiplied the V1 component by sigma 1 and the V2 component by 0. Now assuming that sigma 1 was greater than 1, then we have this ellipse right here. And then we multiply the V2 dash component by 0. So actually this will be squashed in this direction and it will be a 1D line instead of an ellipse. So you will have something like this. You will have some stretched line in the V1 dash direction and it will have no area at all. So this is a combination of points on this axis, or maybe a line if we draw those points continuously. So this circle will be squashed onto some continuous line just like that, and this line will be slightly elongated due to the effect of this sigma 1. After that, you will do this inverse rotation using the matrix U such that the I cap will get mapped to U1. So this might be U1 right here, U1 cap, and we also have U2 cap, but this point will be rotated until all the data points become onto this line, onto this U1 line right here, because all the points were originally on this I cap line, so they will get mapped to components in the U1 direction. This line will just get rotated by this angle right here, but it will still be a line. It will not have an area at all. This drawing matches our result right here, where we only have some components in the direction of U1 cap and we have no components at all in the direction of U2 cap. It is also nice to see from this drawing why the matrix A has no inverse, because from this line right here we could rotate it back to have this line in this space, but we can't turn this line again into a circle. We can't know the original lines in this direction, because this line could have resulted from the projection of this circle and then some scaling, or from the projection of this, let's say, rectangle and then some scaling, or from this rectangle and then some scaling. And so we really don't know how to get the original shape of the points that resulted in this projection right here before the scaling operation. So the best we could do if we want to reverse this operation is get the V1 dash components of the points without the V2 dash. Actually, the pseudo inverse that we will study later in this chapter will try to do just that.